Okay, so I do the lecture today. That's lecture 22, joint probability distributions, 3 expected values, covariance, and correlation. So let's recall, if X has some distribution with PDF, say, or PMF, no difference, PDF fx, then we said expected value of x was integral from minus infinity to infinity x fx dx, and expected value of some function of x was simply integral minus infinity to infinity gx fx dx. And if we have the PMF px, say, then this will be sigma x px over all x, and this will be sigma gx over x. Now we are dealing with more than one variable. So let's say that we have x and y, and we have 2, let's say, because the covariance correlation that's related to 2x and y have some distribution with PDF, say fxy, then given a function g of x and y, well, this function can be what? It can be like x squared plus y squared, something like that. Okay? Like this. So given a function gxy, then we define e of gxy to be the double integral gxy fxy dx dy. And if we are given the PMF pxy, then we have e of g, x, and y to be sigma over x and over y of fxy, no, sorry, gxy, pxy. So that is the expected value of a function of x and y. So it can be something like this. So you are given x and y, 2 random variables, and you write like a linear function of that. You write like, you can say that if gxy can be something like this. Can be like, I don't know, so something like, say, you have 2x plus 5 for the x, plus, say, something for the y, minus 3y, minus, say, 10, something like that. So it is a function of x and y when you multiply by pxy, which is also a function of x and y, and you integrate, and you will get the expected value of that. Okay, so it's like, say, if x is something that at random happens, like toss a coin or roll a die or something, and then you win like $2 or something, plus like 5 bonus, something like that. So that will be your win and your loss, for example, from y. So something like that, and you will get a function. This will be like the money in your pocket left. Can be something like that. So, anyways, now there are many examples in the book, and also nice problems that are assigned. So let's now why do we do this? Why are we concerned about this? This is because of covariance and correlation. That is something which you might have heard a lot. Not this one, but this one. Correlation. And there is, before I give you formulas, there is like a, how should I say that, paradigm, or the way that we do in mathematics. Suppose we have two phenomena happening, like x and y, say something. Like, for example, you have population of, like in differential equations, you talk about population of, say, foxes and population of rabbits, say. And like the predator-prey problem, for example. Then you want to see, you want to model the effect of these two populations on each other. So you have certain population X and certain population Y, and you want to model the interaction between these two. What would be the best model the best, say, way of modeling this interaction? I mean, this X represents like number of foxes, say, and the Y number of rabbits, for example. And what is the best way? Should we add them? Should I say the interaction can be modeled by writing X plus Y, say? Well, can this be modeled with like sine of X plus sine Y? Who knows? Maybe that also works. So it should be something like that. Should I be like cosine XY or something else? But the thing is, most of them, but this one, the problems with this one, you might say, okay, I just don't care about what people say, and I want to develop my own theory. So you write down the interaction like X plus Y, or someone else writes it like cosine X plus Y. Well, this might be a close one to what we are talking about. But what is the simplest that really is simple enough, say, and also good enough to show the interaction? Now, after, I guess this is not just something that they said, okay, let's do this and it works. No, I think it took some time to realize that this might be the best choice. So in mathematics, when we want to just model interaction like that, we multiply them. We write X times Y. Not X plus Y, X times Y. So somehow to model the interaction or to study the interaction, we use this X times Y. Now covariance also uses this, say, paradigm to model the interaction, multiply the two variables. And it's defined this way. First of all, when we are given random variable X with some distribution, then in this distribution, most often it comes with some kind of mean, right? So the parameters, one of the parameters is usually the mean. So mean makes a lot of sense. I mean, it gives a lot of information about the random variable. Yeah, I know, yeah, that standard deviation or say variance also is a huge amount of information, especially about the shape of the distribution. But what does mean do? Mean, it just shows you where it is. So mean, with changing mean, the distribution doesn't really change. It just changes location, right? So mean can be here or can be here, so the location changes. So what we do to get rid of that effect, in a sense, we subtract x from its mean, or the mean from the x, and we deal with this. This distribution has the same shape as x, except it is moved. Where is it now? If we do this, we say that we have centered that at 0. So we have changed the mu is now 0. Mu of this is 0. Why is it 0? Let's check. Mu of this thing, mu of x minus mu is expected value of x minus mu, right? And expected value is like a linear function, so this is expected value of x minus mu. Remember, expected value of constant is constant. This is mu itself minus mu, so it's 0. So if I center a random variable this way, I will in fact get a mu of 0. So it's like just putting the y-axis at this point, at the mu. So just move this thing to left or right. This is like the transformations in college algebra. Remember, subtracting this would move it left or right, depending on what mu is. So it doesn't change the shape. Okay, so let's use this. So if I use x minus mu, and it definitely has some distribution with mu 0. And y, well, let's write mu x here, minus mu y has distribution, some distribution, again with mu 0. Okay. And so let's work with these two. So I want to study the interaction or the effect of these two on each other. So let's say interaction, maybe that's better. So how do I model the interaction? I said interaction is this. So let's multiply that. Then we usually work with, if this gives you something, some kind of, say, distribution, say. I'm not saying that this, we studied the distribution of x times y, that's not easy, but anyway, let's say somehow we know, so we have computed distribution. But then when we have some distribution, one of the things that we find, the first thing that we usually find is what? The expected value of this, or the average of this thing, right? We want to see the average of this interaction. So we find expected value of this. So expected value of this new variable that I have, which models the interaction between these two random variables, this expected value is called covariance. Covariance of x and y. So covariance is the expected value of the product of those random variables when centered. So we say that we have centralized, I don't know if we call it centralized or centered or something. Well, anyway, we have made these two, we have done something so they have a mean 0. Okay, anyway, so this is covariance. So the expected value of the interaction between them as a random variable is called covariance of x and y. Okay, now this covariance, let's use properties of expected value to see if we can come up with another formula, or a much better formula. Or, well, sometimes it's easier to use this, for example. But let's do this. So I have covariance of x and y, and I define this to be x minus mu x times y minus mu y. So I have expected value, let's multiply x, y minus mu y x minus mu x y plus mu x mu y. And I know expected value is like acts like a linear function, so it distributes over these e of x, y. This is a constant, so constant comes out of expected value, ex minus mu x ey plus mu x mu y. But what is this? This is mu x, and this is mu y. So I have mu x mu y, mu x mu y, mu x mu y. So what remains is simply e of x y minus, there are 1, 2, and minus, so it is minus mu x mu y. Or some people just write it this way. E of xy, and this is ex ey, minus ex ey. Okay? So covariance has this also, we can write it as e of xy minus ex ey. Okay, now, so this guy over there, what do you think? What do you see? It is expected value of the effect of x on y in a sense, right? So it's like the effect of how the interaction between them, say, and this is each one separately multiplied. So covariance, in a sense, is measuring how far the interaction, say, in the population is from, say, the expected value of each one of the multiplication. So the interaction of the means, say. So the interaction of the means. So this interaction in a population like this, and that's just the means interaction of the means. Say. Okay, now. So let's see. There's also so this is covariance. So the covariance, well, let me write covariance. Now what is correlation? Correlation, which let me see what the book uses as a symbol for correlation. It uses rho. Correlation, the book uses rho xy. Does it put in parentheses? No. That's xy. I don't know, maybe some places I have seen something else. So that is, in fact, covariance of xy divided by, the book uses a sigma, so it uses sigma. I forgot. Sigma y. And what was sigma? Sigma x is, in fact, a squared was variance of x. And sigma y squared is the variance of y. Okay, so that's correlation. It's interesting. That is the now there is this inequality which I'm not going to prove. It's not simple. It's called the Cauchy-Schwarz. I don't know if there's a theory about it. It says that absolute value of covariance of x and y is less than or equal to sigma x, sigma y. Now, what are these two? These are, in fact, square root of variance. So this is like saying that it is square root of variance of x times variance of y. Right? Sigma x is variance of x square root, and remember, variance is a positive number. That's why I'm writing sigma x squared is variance, so that it means that it's a positive number. Why is it positive? Because it was what? It was x squared, in fact. X minus mu squared. So anyway, so this is telling me that this guy here is less than this. So what is the implication of this? This is an amazing inequality, and the implication is simple. Well, let me erase this and write it here. What happens is this. So the Cauchy-Schwarz inequality is CS inequality. Gave me the covariance of x comma y is less than or equal to sigma x, sigma y. So covariance of x comma y is less than sigma x, sigma y, bigger than or equal to minus sigma x, sigma y. So if I divide by sigma x, sigma y, if I divide by this, which I have it here, so let's divide by this. So what happens if I divide all three sides and they are not zero? Sigma 0 is what? Because you have just a constant, say, distribution. Well, so let's assume that it's not 0, and this is less than 1, bigger than negative 1. So this gives me that correlation is a number between 1 and negative 1. So correlation is a number between negative 1 and 1. Okay, so well, even in a higher level probability, this has a lot of applications, like saying with positive correlation or negative correlation and things like that, or zero correlation. Okay, let's see. So this is correlation. Well, I wanted to add, in fact, I emphasized from the beginning, when they talk about correlation you might have seen that everywhere, like online and in the news, blah, 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 they say there's a correlation between this and that. Well, there's one, say, experimental correlation, the formula, you probably have seen that in the first chapter. And there's also this definition, that experimental is also when you multiply the two. So you multiply the two values. So as you see, this is like a model. So a model has given us some insight into what is happening in nature. So, and there's also some, say, danger here, because you can just write down two random variables, just write some values, and they use the formula for experimental or empirical correlation, which is in chapter 1, I guess, and you can find the correlation. You just find 0.5 saying, oh wow, so these two random values are correlated. So, well, in higher level stats or probability, there are some remedies to this, but if you just pick two samples and find the empirical correlation, and you will find the numbers, and wow, these are correlated, or if it's positive or it's negative, you say no, they are negatively correlated or something like that. Which they might not have any relationship, just something from Mars and the other one from who knows, like in the middle of the ocean, say. But you will find something. But the point is that this is just a model, right? There are a lot of things like this on statistics. This is one of them, that you try to capture something from the data. You want to understand something from the data, and you use a model to capture that. Now this is capturing, as it says, correlation. So it is capturing that relationship between these two, the correlation, you see. And It's defined for two. It's amazing. It's defined for a pair of random variables. Now, let's see what happens if these pair, if they are like independent. So what happens when the two are independent? So let's say that let x, y have some distribution with PDF. Let's go with PDF, not PMF. PDF fxy. Okay. So the PDF is fxy. Assume that x and y are independent. Remember what happened when they're independent, then fxy was, it would split into the two marginals. Okay, so it would split in this form. So if fxy is like this, let's see what happens to covariance in fact. So let's find covariance using this. So covariance was E of xy minus EX EY. So let's find E of xy. We know this by definition is this, minus infinity, infinity, minus infinity, infinity, x comma y, x times y, f of xy, dx dy. But this, I know that this splits. This guy here splits. Minus infinity, infinity, integral minus infinity, infinity, x, y, fxx, fyy, dx, dy. Okay, so well, since it's completely split, also this is multiplied, so that's the product, so I can split these two. This is minus infinity, infinity, x, fxx, dx. This has nothing to do with y, so it's like multiplying them. So this is times integral minus infinity, infinity, y, fy of y, dy. But marginal is like, this is, we look at x separately, or we look at y separately. I mean, so what is this? This first one is ex, in fact, and the other one is ey. Okay. So what happens to covariance? Covariance of x comma y will be ex ey minus ex ey, which is 0. This also gives me a correlation, rho xy, 0. So if the two random variables are independent, we can say that they are not correlated. Correlation of 0, we can just use the terminology uncorrelated or not correlated, uncorrelated usually. So independence implies not correlated, okay? So we can write this up here. And what happened? Why does this happen? Because of the split of this. Because the fxy splits in two. That's why it happens. So that's again mathematics. So, well, you can say, well, it makes sense because of the terminology we are using. Because we're using this correlation, and independence means they are not related. So if they are not related, the correlation should be 0. So even using the terminology or common sense, that makes sense. But in fact, that is just mathematics. But anyway, this is mathematics that makes sense. Okay, so anyway, so if x and y independent, this implies that rho x comma y is 0. But rho x comma y 0 does not imply independence. Unless something happens. Like one of them is that if they are both, they have joint distribution, that's crucial to have joint distribution, and that joint distribution is, say, normal, and then this implies. So, but not in general. In general, that doesn't imply. So, in very special cases, it implies that. But anyways, if you just use some discrete distribution, I used to know some simple distribution. I forgot the discrete one, such that the numbers were so arranged that this would be you would get 0. They were not independent, but you would get 0 because of the numbers would just add up to 0. The covariance was 0. So, but they were not independent. I can't recall that. I might have written it somewhere, but you can just Google it and find correlation equal to 0 does not imply independence. So, example for that, something like that. So, but the other way around is correct. Okay, now. What else? Let me check and see what else we have in this section, the correlation and discourse. Oh yeah, so let's say, I remember that 24xy. So let's try this example that we did last time, that was the 24xy example, and find the correlation. So it was x, y, PDF. So remember the PDF was like this. Was 24xy for x and y between 0 and 1, and x plus y less than 1. And 0 otherwise. So let me not write that 0 otherwise. So what happens here? Let's find the covariance of this thing, covariance of x comma y. That is e of xy. Sorry, x times y. E of x times y minus exy, right? Minus ex ey. Okay, so I guess we found f xx was I have it here, in fact it's in the book. So 12x times and I guess the y was also the same, right? So fy y was also the same. Not the same, similar. Because okay, so we have everything ready to find ex, ey, and exy. So what is exy? Exy is simply integral where it is 0 and 1, this one, and the other one, remember it was 0, 1 minus x. Okay, so that is the triangle. Remember that is the triangle. 0, 1, 1. And then I have xy times fxy, 24xy which one is inside? That is x, this is y. Dx. Okay, so that's xy, 24xy dy dx, and I guess the book has calculated this, didn't it? 2/5. 2/15. And Ex is integral from 0 to 1, that is x fx. What is fx? Times 12x, 1 minus x squared. Is it 1 minus x squared? Yeah, that square is up here, sorry. 1 minus x squared. That's what we found. So 1 minus x squared dx, and if you do you calculate this, that's 2/5. 2/5, and that's also equal to e of y. Ey is the same thing, except it is y, is the same formula, and you will get the same answer. So put all these things together, we can find its covariance. So covariance of these two, xy will be e of xy minus ex ey. So that is 2/15 minus 2/5 times 2/5. 2/15 minus 4/25, which is minus 2/75. Okay, so that is this thing. Okay. Now I haven't calculated this variance, and you can just do it yourself. But anyway, that covariance is negative, and you will get a negative correlation, in fact, because rho, sigma x and sigma y are positive numbers. So the correlation of this thing is negative. It's just interesting that rho xy is minus 2/75. Sigma x, sigma y is negative, because these two are positive. So that is a negative number. Negative number bigger than -1. It's bigger than -1. We know that it's bigger than -1. So they are negatively correlated. That's interesting. They are negatively correlated, these two, with this PDF. Okay. Well, let me see if there is anything else that I should add here. Oh yeah, well, let's see what happens if I have some functions of x and y, and what happens to covariance. So let's say, let's just go, what is covariance of, so let's say A, B, C, and D, real numbers, say, and fixed, so they are not random. And let's find covariance of ax plus b, comma, cx plus cy plus d. Okay, so a linear function of the first one, and also linear function of the second one. Okay, so what was the formula? The formula was expected value of this thing times cy plus d minus expected value of each one times each other. A ax plus b, expected value of cy plus d. So what do I have here? So I have a c x y plus a dx plus b c y plus b d. Minus this will be simply a ex plus b times c ey plus b. So here I have a c exy plus a d ex plus b c ey plus bd minus what do I have here? A c ex ey this one times this one minus a dex minus b c ey minus bd. Okay, minus plus, and they cancel out, and the only thing that remains is ac times e of x y minus ex ey. So that is a c times covariance of x comma y. Okay, so you can see that the b and d, they do not come into the picture. It's just a coefficients of x and y, they contribute to this. What is it? If we fall into model sign. And there is another thing which I mentioned most of everything except this one. So let's so that's what happens to covariance, and then the correlation also. Well, let's find correlation and see what happens to correlation if I do that. So I have a C covariance, and let's see, I have sigma x, sigma of ax plus b is square root of variance of ax plus b. So which was what? Square root of variance was what? This is a squared variance of x. So it's a squared, a sigma variance of x, so it is a sigma x. The same way, sigma of b, cy plus d will be c sigma y. So correlation of ax plus b, comma cy plus d will be simply, if I write it, AC covariance x comma y over this a sigma x b sigma y, so it will be covariance of xy over sigma x sigma y, and that is correlation of x comma y. So it's interesting that if I have a linear combination here, then I will get that. It doesn't change anything if I just find them. Just multiply this by a number and add it to another number, the correlation doesn't change. So, but the covariance changes by AC. But when you divide it by the sigma x, sigma y of the new variables, then these constants cancel out, and this correlation becomes the same thing. And now another thing which is interesting, so we realize that sigma x is 0 when they are independent, but not conversely. So when sigma x correlation is 0, it doesn't mean that they are independent. Now there's another one. What happens when the correlation is 1 or negative 1? In fact, if rho is 1 or negative 1, then one of them, say y for example, is a linear combination of the other one. Then y is ax plus b for some a and b with a not equal to 0. Okay, so let's see what happens if I let's just go backward. Let's say we have x and we have y, which is ax plus b. So let's find the covariance of these two, x comma ax plus b. We just found the formula for this. That was one. That was a covariance of x comma x. It's interesting to see what this one is. So covariance of xx. So that is a times exx minus ex, right? So that is a. And why it's not a? Because there's a 1 here, right? A times 1 covariance. So this is what a times e of x squared minus e of x squared. What is ex squared minus e of x squared? That is variance of x. In fact, this covariance of xx is variance of x. Okay, so this gives me a times the variance of x. Okay. And let's see. So this is that's covariance of this. And what is sigma x and sigma the other one? So sigma of x is sigma x. Sigma ax plus b is remember that was this. I should have written this variance of not variance. This is this. Let me write it again. So that's sigma a squared variance of x. I shouldn't have written a over there. It is because I assume that a is positive. But if a is not positive, this is absolute value of square root of variance of x. So that's absolute value of a sigma x. Okay? That's absolute value of a sigma x. So what happens then to correlation between these two? Let me sum up everything. So the correlation between these two, relation between x and ax plus b. On top I have this, a times variance is what? Variance is sigma x squared. Sigma x squared. In the denominator I have sigma x times absolute a sigma x. So what happens? That is simply a over absolute a. A over absolute value of a when a is not 0 is either 1 or negative 1. Depends on a, right? So if a is positive, that's plus 1. If a is negative, that's negative 1. So this is in fact either positive or negative, depending on a. It is either positive, so this is plus 1 when a is positive, negative 1 and a is negative. So correlation between these two is either plus 1 or minus 1. Now the other way around, I don't see how we can show that when the correlation is 1. In fact, that is not in the back of my mind how we can go backwards. But forward, when we assume that this is in fact a linear combination of x, then this is what happens. It's either 1 or a negative 1 depending on that the coefficient A. Okay, so that was the section on variance, covariance, and other things. And so let me stop this thing and see you tomorrow.